Hello everyone, and welcome to this video for section 9.2 on series and convergence. So we've just dealt with sequences, and now we'll get into series. So our objectives for this particular video are: number one, understand the definition of a convergent infinite series. What does it mean to be a convergent infinite series? Number two, use the properties of infinite geometric series to determine a convergence or divergence. And number three, use the nth term test for divergence of an infinite series. Now, the first thing we have to do is have an understanding about what a series is. So if we take a sequence, this a sub n sequence, and we go through and make it into a summation, so we have n equals 1 to infinity, the sum of that, of a sub n, this is what we're going to get: a1 plus a2 plus a3 plus a4 plus a5, and so forth. And that is what's called an infinite series. We're adding up the terms of that infinite sequence. Now, one of the things that happens when you do this is you have what are called partial sums. And the notation for a partial sum is s sub n. And so what that means is it's going to be the sum of the first n terms of that particular series. So S1 is just A1. S2 will be A1 plus A2. S3 will be A1 plus A2 plus A3, and so forth. Okay, so what's going to happen then when we do that? This is going to go through these values of S1, S2, S3, and so forth are actually going to form a sequence, and that sequence of partial sums there. Now that particular sequence is going to converge or diverge. And so if this sequence of partial sums, if that converges, then the series converges. So if that sequence converges, then the sum converges. And the same thing would be true about if it diverges. Okay, if that sequence diverges, then the sum that we're looking at is going to diverge as well. So now let's take a look at an example here. In this case, I'm taking the sum as n goes from 1 to infinity of 1 over 2 to the n. So it's going to be 1/2 plus 1/4 plus 1/8 plus 1/16 and so forth. And if you take a look here, we have some of the partial sums. 1/2, S1 is 1/2, S2, when I take 1/2 plus 3/4, or 1/4, I'll get 3/4, sorry. When I take S3, 1/2 plus 1/4 plus 1/8, I'll get 7/8, and S4 is 15/16. And I could generate more by going through and adding more terms. But the main thing I want you to recognize on this, at this particular point, is that these sums, S sub n, I can look at this, look at these terms, and I notice some things with that one. And what I notice on that is that these terms are all equal to 2 to the n minus 1 over 2 to the n. You'll notice that the numerator is always 1 less than the denominator. And so it would make sense that, and in terms of the denominator, we're always going up we're multiplying by 2, so we get that. And so what I can do now to determine whether or not this series converges or not, I can just take the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n. Well, in this case, you have one of two things you could do. You could recognize on here that as n gets very, very large, that this 1 is going to become less and less significant. It's basically going to be insignificant, which would then result in this approaching 2 to the n over 2 to the n, which would be 1. Or you could just go to L'Hopital's rule. We know that as n goes to infinity, that's going to be infinity minus 1 over infinity. That would give us, in this case, infinity over infinity. And so I could then go and take the limit as n goes to infinity of the derivative of the top and bottom. Well, the derivative of the top is going to be 2 to the n times the natural log of 2 minus the derivative 1 is 0. So it'll just be 2 to the n natural log of 2. And the same would be true for the denominator, and that's just going to end up being 1. So in this particular case, we know that our series, this series up here, it is going to converge to 1. Take a minute, make sure you're comfortable with all the information here, and once you're ready, we'll move on. Now, here's another series. Now, this one is called a telescoping series, and you'll see why in a second. But we start out with the given series right here, n equals 1 to infinity of 2 over n squared plus 2n. So with this particular series, I can go through on this one, and I can use partial fraction decomposition, and I can rewrite it in this form. Okay, so that's where I'm going to go. I'm going to go right there. Now, I go on this one, and I start going through. Let's do a term by, we'll go through and find our partial sums. And what I notice on here is that when I let n equal 1, I get 1 minus 1/3. When n equals 2, when n is the second term, so I'll get 1 minus 1/3. And then when I go to add in the second term, I'll have the 1 minus 1/3, that first term, plus our second term, which would be 1/2 minus 1/4. So really what's happening on here, let me put some parentheses in here. I'm going to have parenthesis and parenthesis. And here's the first, second, and then third. And finally, we have our fourth term. And so when I take a look at that sec s sub 2, it's going to end up being these two added together, but I'm going to rearrange this a little bit. That's going to be 1 plus 1/2 minus 1/3 minus 1/4. I'll put the addition first, subtraction second. Now interesting things happen after this. On this particular one, I take the sum of my first 3 terms, but you'll notice here the 1/3. I have a minus 1/3 and a plus 1/3. So those are going to cancel out. So when I do that problem here, these two will go away. And so what I'll be left with is 1 plus 1/2, still the addition, but now I'll have a minus 1/4 minus 1/5. So we have that. And when I deal with the s sub 4, the same thing is going to happen. The 1/3 again drop off, but also you'll notice the 1/4 drop off. And so s sub 4, in this case, becomes 1 plus 1/2 minus 1/5 minus 1/6. So with that, we can start going through and saying, well, what do we get? What's going to be our general term for our sums? So in this case, s sub n, we know, you'll notice everything is 1 plus 1/2, except for s1. Is going to be 1 plus 1/2. But then you'll notice when I had s sub 3, I was minus 1/4 minus 1/5. 4 is 1 more than 3. 5 is 2 more than 3. When I had s sub 4, I have 1/5 minus 1/5 minus 1/6. 5 is 1 more than 4. 6 is 2 more than 4. So what I get on this one is that this is going to be, s sub n is going to be 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. And this is going to be true when n is greater than 2. As long as n is greater than 2, that's always going to be the case, because that's when, or actually when n is greater than 1, sorry. When n is greater than 1, that will always be the case. So in this case, what's going to happen is if I take the limit on that as n goes to infinity, I get 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. Well, as n goes to infinity, 1 is going to go to 1. 1/2 is going to go to 1/2. But now these two pieces here, as n goes to infinity, I'm getting basically 1 over infinity plus 1 and 1 over infinity plus 2. Both of those for whatever, all intents and purposes, we can think of those as 0. And so in this case, the sequence of partial sums is going to converge to 3 over 2. And so our series, this particular series, converges to 3/2. Again, take a minute, look at these look through this problem, make sure you're comfortable with everything I did, and then once you are, we can move on. Now let's take a look at a geometric series. Now, a geometric series is a series where it's, in this case, we have n equals 0 to infinity of a times r to the n power. And so what's happening here, if you remember from your pre-calculus days, a geometric series is where we're multiplying by the same amount every single time. And that amount is generally labeled as r. It's called the common ratio. So if I go through and expand this particular series, when I put 0 in, I'll get a plus a times r plus a times r squared plus a times r cubed plus a times r to the fourth, and so on. So when I take a look at my partial sums, my first s sub 1 is just going to be a, which is a times 1. Now you'll see how I'm putting this on there. S sub 2 is going to be a plus a times r, which would be a times 1 plus r. S sub 3, a plus ar squared, and then when you pull out the factor of a, you get that. And S sub 4, when you expand find the sum of the first 4 terms, you'll notice you get this. Now, one of the things you have, if you remember from your pre-calculus class, we had formulas for the partial sum of a geometric series. And that partial sum, that formula, what we do to go and get that formula, what we did is we're using this fact right here. That if I take 1 minus r times 1 plus r squared plus r cubed plus all the way down to r to the n minus 1, if I multiply that out, if I was to go through, distribute the 1, distribute the negative r, combine all the like terms, I'm going to get 1 minus r to the n. And so what we have here, basically what we're doing is we're multiplying this by top and bottom by 1 minus r. So I get that the partial sum is a times 1 minus r raised to the n power over 1 minus r. Now that's the partial sum. Okay? And that works for any particular series. Doesn't matter, geometric series. Doesn't matter what r is. But something interesting happens if we go through and restrict r. What you need to remember, the key thing to remember, if I take a fractional amount, a number whose absolute value is less than 1. So I'm going to go through and restrict r to be where the absolute value of r is going to be less than 1. Okay? Now r can't be 0. Okay? We have that. But the absolute value of r has to be less than 1. So what we're looking at here are fractions like 1/2, 2/3, 9/10, negative 3/5. Those types of values for r. If I limit that into that situation, then if I take the limit as n goes to infinity of r to the n power, that limit, because it's a small number, it's something smaller than 0. When I take powers of numbers, or something that's where the absolute value is less than 1, if I take powers of things like 1/2, if I just take higher and higher powers, those values are going to 0. So what happens is as n goes to infinity, if the absolute value of r is less than 1, as n goes to infinity, r sub n is going to go to 0. And so if the absolute value of r is less than 1, the limit as n approaches infinity of s sub n equals a over 1 minus r to the n over 1 minus r is going to go to a over 1 minus r. Which this now gives us our theorem. We have a geometric series where the absolute value of r is greater than or equal to 1. We know that series is going to diverge. If the absolute value of r is between 0 and 1, then the geometric series and what we do know is that the sum of that series, The sum of that, where it's going to converge to, is going to be a over 1 minus r. Now, the other thing you have to keep in mind here, this is where some mistakes happen. When you're doing this, okay, this is a form of the geometric series. But when you're working on these things, what I work with when I'm working on this one, I will always go and write out an expansion of the first few terms. So in this first example here, we're taking the sum as n goes from 1 to infinity of 2 times negative 3 over 2, negative 3 halves to the n power. So on this particular problem, we know that r equals negative 3 over 2. The absolute value of r then is equal to 3 halves, and that is definitely greater than 1. So therefore, we know that this series here, n equals 1 to infinity of 2 times negative 3 over 2 to the n power, we know that diverges. Our next one is n equals 2 to infinity of 4 times 1/3 to the n power. Now, here's the thing. This is where we have a little bit of an issue. Because you look at this, we know on this particular problem, I know r is 1/3. And since r is 1/3, 1/3, the absolute value of 1/3 is less than 1. So I know I'm looking at a convergent geometric series. And so the next thing we're going to ask you to do is find out where it starts. Okay? Now, often what students do is they just remember this form right here. A times r to the n. And they say, oh, that number there goes here. So they look at this and they say, oh, that number is there. No, it's not. Because this one is starting at 0, we're starting at 2. So what I always tell people to do on this is to write out the first few terms. So when I put in 2, that's going to be 4 over 9, because it's starting 2 to infinity. When I put in 3, I'll get 4 over 27, plus, when I put in 4, 4 over 81, plus, and that will continue on. But the main thing I want you to recognize on this one is the a value is always that first value that you get in the series of numbers you're adding. So in this case, a is 4 over 9, r is 1/3. So I know that this series is going to converge, and it's going to converge to s equals 4 over 9 over 1 minus 1/3, which is 4 over 9 over 2/3. And so that's equal to 4 over 9 times 3 over 2, which equals, again, 2/3. So in this case, this particular series is going to converge to 2/3. Take a minute. Make sure you're comfortable with the calculations I did here. Also, the one thing I want to make sure that we're comfortable with is the fact that, yes, this right here and this are the same value, but that is a coincidence. Okay, that will not always be the case. Okay, so take a minute, make sure you're comfortable with everything. Once you are, we can move on. The last thing we get is what is really the most misused of the tests that we have. Okay, and the reason it's a problem is because we're taking a limit and we're looking at what the terms of the sequence with this one. And so often when people are working on this thing, they will mistaken what it's actually saying. So in this case right here, we're going to let the actual thing is the nth term test. It is a test for divergence, not convergence. It does not tell anything about convergence. We're going to let a sub n, this series, n equals 1 to infinity of a sub n, be an infinite series. If the limit as n approaches infinity of a sub n does not equal 0. So I take the limit of these terms of that sequence. If I take the limit of that sequence and I don't get 0, then I know the series diverges. Guaranteed to diverge. If we get 0, we know nothing. We can't say it converges. We can't say it diverges. Okay? But if that limit does not equal 0, then it diverges. And that's where the problem comes in, because a lot of times people will go through and think, oh, well, that means they'll start thinking, okay, that limit is equal to 0. That's not going to say that it converges. If you have to go through and tell yourself, anytime you're looking at the terms of the series of that particular sequence, a sub n, that if you're taking the limit of those values, if that equals 0, you've got to go through and remind yourself, you do not know anything about whether or not that series is going to converge or not. Okay, but if it does not equal 0, then you know it's going to diverge. Okay, guaranteed. And so remember on that one too, you can see that also gets another little bit of an issue, because when we have a series, if I had this series, n over 2n plus 1, if I go through on that, I take the limit on that as n goes to infinity of n over 2n plus 1, I know that's going to come out to be 1/2. That this particular sequence of values converges to 1/2. But because that's a 1/2, I know the series n equals 1 to infinity of n over 2n plus 1, I know that diverges. Another one we could have, let's say I have the series n equals 1 to infinity of 2 to the n over n squared. Okay, so I look at that one. And I can take that one, I take the limit on that as n goes to infinity. I get 2 to the n over n squared, which would be infinity over infinity, which I can use L'Hopital's rule. Well, that's going to end up being equal to the limit as n approaches infinity of 2 to the n times the natural log of 2 over 2n. And again, as n goes to infinity, that's going to end up being infinity over infinity. And so I can do L'Hopital's rule again. When I do that, I get in this case, I will get the limit as n approaches infinity of 2 to the n times the natural log of 2, that thing squared, over 2, which in this case is infinity. So therefore, I know that series also diverges, because that limit was not equal to 0. Again, make sure you're comfortable with this, and really put this in your notes to stress that this is a test for divergence, and to never go through and look at the term values and say, oh, those term values are going to 0, so it converges. That is definitely not going to be true. So with that, this does conclude this video. Again, if you have some questions, write them down in your notes, ask them, and we can ask them in next class. So with that, see you in next class.